So this problem here is asking us to find the magnitude and location of the equivalent point loads, and then using those we're going to want to find the reaction forces at A and B. So we have two different distributed loads here. We have load 1 and load 2. So we're going to want to know the functions for each of the loads. So our first plan of action is to start off finding the function of our first point load. So to find the slope, we're going to do rise over run. So we're going up 2 kilonewton per meter over 6 meters. So we're rise over run. We're going up 2 over 6. So 1/3 is our slope. So 1/3 x. And then we're going to want to add 4 because we're starting off at 4 over here. So that's like our b value where it intercepts the y-axis. And then we're going to want to do the same thing for our second distributed load. We're going to want to find the function of that one. And that's the same thing. We're looking at how much we cover, what's our slope. So we're going down -6 kilonewtons per meter over 6 meters. So our slope is just -1, so negative x. And then you're going to want to do a little bit of, you can just solve this using this like beam itself. This makes it pretty easy because it's just our slope is -1. You'd want to find out where would intercept the y-axis over on this side. So since our slope is -1 over 6 meters, it's going to be going like this. This is what it would look like. And we're just happening to like cut it off right here. So this is our 6 value. And if our slope is -x, you're going to want to find what's this point. So this is easy. They're both 6. So you would just add 6 to 6. So your value up here would be 12. Because when you do it this way, you're going to figure out 12 times what times x, what times -x is equal to 0 over 12 meters. So when you think about it like that, you figure out that the intercept on the y-axis would be positive 12. Okay, so you could use y equals mx plus b. I just kind of like figure it out conceptually, but either way works. So from here, we're gonna want to take the integrals of these because that's gonna be what gives us our equivalent point. So our equivalent point, and we're gonna want to make sure that we add these together because these are both acting on the beam. So, and this is only spanning from 0 to 6. This is our like origin. This is our starting point over here. So that's going to be our 0 value. So 1/3 x plus 4 dx plus the integral from 6 to 12. And that's because this whole thing spans 12 meters. And we are starting over here where it's already 6, and we're going to add another 6. So this value is going to be 12 meters from the origin point. And we're going to plug in this equation, -x plus 12 dx. Okay, and then from here, this is just taking the integrals. This is just pretty much straight calculus. This is going to be 1/6 x squared plus 4x from 0 to 6. And for our next point, we're adding -x squared divided by 2 plus 12x. And this is from 6 to 12. And then you're just going to want to plug in, this is just plug and chug, 1/6 times 6 squared plus 4 times 6 minus, and then you plug in 0. So when you plug in 0, it's just going to give you all 0 terms. So minus 0 plus negative 6 squared over 2 plus 12 times 6. And then, oh, sorry, this is not 6. This is 12 right here. 12 squared, 12 times 12. Then we're going to do the 6. So minus negative 6 squared over 2 plus 12 times 6. And then doing that, we get our equivalent force is 30 minus 0 plus 72 minus 54. Force equivalent is 48 kilonewtons. So that's our equivalent force. And so our next step is that we're going to want to find where that is on our beam. Okay, so now to find the spot where the equivalent force is on the beam, we're going to do our equation for our x of the equivalent point load. And this is our equation. So this is using our functions that we found for distributed load 1 and distributed load 2, and we're multiplying those both by x, but we're still going to take the integral of those, and we're going to divide all of that by our equivalent force. So that's going to look, this is what that's going to look like. From 0 to 6, y, or x minimum, x max, and this is for our first one, 1/3 x plus 4, and this is multiplied by x. And from there we're going to add 6, 12, and this is our, for our distributed load 2, negative x plus 12 times x. And this is going to be divided by our equivalent force, and that was 48 kilonewtons. So from there, this is just geometry. This is just algebra at this point. 6 to 0, 1/3 x squared plus 4x plus 6 to 12, negative x squared plus 12x divided by 48 kilonewtons. X equivalent is equal to, and then you're just going to want to take the integral of these. So you're going to get 1/9 x cubed plus 2x squared from 0 to 6 plus negative x cubed divided by 3 plus 6x squared, and that's from 6 to 12, and that is divided by 48 kilonewtons. And there again, it's just going to be plug and chug. X equivalent is equal to, so you just plug in the values like we did before, doing the same ways. So it ends up getting you 96 minus 0 plus 288 minus 144 divided by 48 kilonewtons. And then we end up getting our point of where it's going to be our x equivalent is going to be 5 meters. So that's going to be 5 meters in on our beam. So now that we have our equivalent, the equivalent point load, we have the force and where it is. From there we can go ahead and we're going to redraw our free body diagrams, and then we're going to solve for reactions at A and B. So from here we're going to redraw our free body diagrams. So our equivalent force was 48 kilonewtons, and our x for that is 5 meters. So I'm going to start to redraw our free body diagram. So we have this upward force. This is our reaction at A. And then we also have our reaction at B. Both going to be upward. And we're just going to draw our equivalent point load here, where that's all we're going to need to draw. We already solved. We don't have to take into account these distributed loads. We're doing that by using the equivalent point load. So that's going to be 48 kilonewtons, and that's 5 meters from A. So doing this, we can do our free body, or we can use our equilibrium equations to solve for reaction A and reaction B. And then it's just 12 meters between reaction A and reaction B. So first we can take our equilibrium at Y, which is equal to RA plus RB minus 48 kilonewtons, and that's going to equal 0. So we have that. We can't really solve for anything yet, but from here we can take the moment at A, which is going to be, so if we have the 48 kilonewtons down, that's going to create a clockwise rotation. So that's going to be negative 48 kilonewtons times 5 meters. And then we have our reaction at B. That's going to create a counterclockwise rotation, so that's going to be positive. Our reaction force at B times 12 meters, because that's 12 meters apart, and that's equal to 0. And from there, we can solve for our reaction force at B. Reaction at B is equal to 48 times 5 divided by 12. So that's giving us our reaction force at B is equal to 20 kilonewtons. And then from there, we can plug reaction B into this equation. So RA plus 20 kilonewtons minus 48 kilonewtons equals 0. And then that we get reaction force at A is equal to 28 kilonewtons. And these two, reaction at A, reaction at B, those are our answers for the problem.